Which one of the following particles has the biggest size? We have sodium ion, magnesium ion, fluoride ion, and neon atom. So we're talking about atomic or ion size here. Now, if this is atomic size, if all four particles are atoms, it's pretty easy for us to follow the periodical property of atomic size and say, since sodium is on the left side of the periodic table and of all four of them on the lower level, the sodium would be having the biggest size. That's what periodicity says. But we're not dealing with neutral atoms. We're dealing with ions. And that makes things a little bit more complicated. To check out the size, let's first think about the electron configuration. Because eventually, how far is the valence electrons to the nucleus? That would determine the size of atoms. So, let's go. Sodium plus. Sodium has 11 electrons, losing 1. Now you got 10. 1s2, 2s2, 2p6. Magnesium, 2 plus. Magnesium is number 12 on the periodic table. And losing 2, you got 10 electrons. 1s2, 2s2, 2p6. Fluoride is number 9 on the periodic table. Fluorine is number 9 on the periodic table. Fluoride ion got 1 extra electron, so 9 plus 1, also 10 electrons. And then neon. Number 10 on the periodic table is a neutral atom, 10 electrons again. Oh, all four particles actually have the exact same electron configuration, so they're isoelectronic. When they have the same electron configuration, does that mean they would have the exact same size? Is this a trick question? No. Although they have the exactly same electron configuration, and electrons are all the same. Now, don't forget, inside, in the heart, they're different. They have different nucleus, and different nucleus have different charges and different kind of attraction on the electrons. After all, that's what's holding the electrons together. That's what's holding the atom together. Yeah. Well, but who's attracting it harder? Yeah. To be able to answer that, we need to have our, instead of atomic number, effective nuclear charge. Yeah. The way that we calculate our effective nuclear charge is atomic number minus number of core electrons. Anything, any electron that's not in the valence shell is a core electron. And you look at the 1s2, 2s2, 2p6 setup. Apparently the 2s, the second shell, that's the valence shell. Because that's the outermost shell, that's the shell with the highest number up front, however you want to say it. And that makes the 1s core electrons. And for each of them, you have 2 core electrons. Yeah. But they do have different atomic number. Sodium, 11 minus 2. Magnesium, 12 minus 2. Fluorine, 9 minus 2. And neon, 10 minus 2. So we have 9, 10, 7, and 8. Now after we get the effective nuclear charge, how do we determine the biggest size, the smallest size? Now, remember, effective nuclear charge represents how much real attraction the nucleus has over the valence electrons. The stronger they attract them, the closer the valence electrons would be to the nucleus, and since the average distance of nucleus, valence electrons to the nucleus determines the size of atom or particle. Whoever have the strongest attraction would have the smallest distance and would have the smallest size. So whoever have the weakest attraction, which means the lowest effective nuclear charge, would have the biggest size, because the nucleus couldn't control the valence electrons as good as the others, and they have a chance to go further to make your atoms bigger. Using this rationale, now the answer is obvious. 7 is the lowest effective nuclear charge, and fluoride ion is the biggest particle in the group. So using the effective nuclear charge, we can very easily determine for the isoelectronic particles who has bigger size or smaller size.